I myself solve some problem for the students in order to understand the concepts.
Yeah, that way you can, yeah, that way you can keep on brushing up the subject and
Yes,
uh,
yes, madam. Yes, madam.
keep on being in touch with the subject. Yeah,
Yes,
that's a
yes.
good thing, since EMT is not only like conceptual, but it has so many formula and so many laws and everything. So you, once you read EMT, then again for teaching EMT you have to keep on brushing the subject again.
Yes, madam. Even by next semester, I forgot a few things, and then I have to refresh myself in order for going the classes.
Yeah, that
Mm,
would have happened. I can
yes, yes,
understand.
madam.
Okay, okay. So let's start the session then.
Yes, madam. Sure, madam. Thank you. Fine.
Yeah, so I have changed my background this time. Yeah, so hello everyone. I think uh, baby Yada Mari is you have joined for the first time. I think the session you have joined for the first time. So I will introduce myself first. I'm Vishakha Pandey. I'm from IIT Bombay. I'm doing PhD. I'm in third year from electrical engineering. So today we will be solving week 8 assignment 8 for from previous year, and there will be around 10 questions to solve. So we will be solving those questions. uh, our primary focus is so that to tell you the what how to solve these kind of questions, and it will help you in the this time's assignment. So that's why we, this is our primary goal, is that you are able to solve this type this year's question, and also some concepts that still you what concepts you can use to solve these kind of questions. Okay, so let's go ahead. Yeah, so I'm sharing my screen now. Okay, so week 8 assignment 8. All right, so the first question is, a lossless transmission line is 60 centimeter long and operates at frequency of 400 megahertz. A line parameters are L is equals to 0.36 microhenry per meter and C is equals to 100 picofarads per meter. Using the information to solve questions 1 to 3, the characteristic impedance is. Okay, so the first question here is, in the first question, what uh, the most important thing that you need to notice is the transmission line is lossless, right? Okay. Another thing is it is operating at a frequency of 400 megahertz, then L and C, right? And what is asked here? A characteristic impedance is asked. So characteristic impedance is asked from us. L is given, C is given, frequency as well as the length of the transmission line is given to us. Okay, frequency of operation. Yeah. So can someone from you tell me how to solve this question?
Madam, characteristics impedance means is it not, but I don't know how to solve. Is it not
Yeah.
characteristics impedance?
Hmm. So
Root
first,
L by C, ma'am.
yes, good. Why root L by C? Because the transmission line is lossless, right? So for lossless transmission line, we know that characteristic impedance is Z naught is equals to root L by C, right? So we know the formula for a lossless transmission line. Z naught is equals to root L by C. We know L is equals to 0.36 into 10 power minus 6 Henry per meter. We have converted into SI units, right? LNC per meter, okay? Henry per meter and Farad per meter. And we have put it here in the formula. and we got 0.36 into 10 power minus 6 upon 100 into 10 power minus 3, 12, that is 3 ohms, right? Is there any confusion here?
No,
Pretty
ma'am.
simple. It's in lecture.
No, ma'am.
Yeah. So here you can see it is in lecture number 59. Here you can see for Z naught, for lossless case, right? Z naught is root L by C. Okay. So let's go to question number 2 then. Okay. Now the question number 2 is the phase constant is. Okay. So in the same lecture, which has been taught to you by NPTEL, if you have done the NPTEL session, you would know. So for lossless case, our gamma is j omega root LC, right? For lossless case. So again, uh, yeah. So phase constant beta is asked to us, right? And we know that propagation constant alpha, propagation constant gamma is can be given as alpha plus j beta, right? Here j beta is beta is phase constant and alpha is attenuation constant, right? So we will put r plus j omega l g plus j omega c under root whole under root is equals to propagation constant, right? And since it is a lossless, we know it's the transmission line is lossless, then r will be 0, right? So it will become j omega root lc. So beta will be, here propagation constant has imaginary term, so this whole term is imaginary, so our beta will be equals to omega root LC, right? We know omega, that is we can convert, here we know the frequency, right? 400 megahertz, we can convert it into omega. So we know that 2 pi f and then root LC, right? So this is, we got 15.08 radian per meters, right? Here 15.08 radians per meter, section option B. So is there any issue here? It's a pretty simple formula based question, right? If you know lossless transmission line, for lossless case, what is the propagation constant, what is characteristic constant, what will be the formula, you will be able to solve these questions. And these questions are for 2 points each, 2 point this, 2 point this, yeah. So pretty simple questions, and you will be getting marks, like double the marks for the efforts, yeah. So, right? Do you have any doubt here? Or should I go ahead?
No, ma'am. Clear.
Okay, okay, good, good, good. Okay. Now the input impedance for ZL. So load impedance is given to us, which is 150 ohms. Okay. ZL is given to us, and input impedance is asked. Input impedance is Zin, right? So, so Zin is asked and ZL is given to us. Let's go. Can someone tell me how to solve this question before going to the solutions? Okay, no problem. Here also lossless case is given, right? In the question, it was written that using the information solve questions 1, 2, 3, right? So the transmission line is lossless. This you have to remember. This question, let's go and see if we have something from here that we can use, and then we will go to our solutions, right? Okay, let's go to assignment 60 and see if we have something. Yeah, so we have simplified expression for Zin for lossless case, right? and this is the simplified expression. So so rather than using tan beta L, we can use cos here, cos beta L here, and sin beta L here, right? Something like this. So input impedance is asked to us, and load impedance is 150 ohm, which is given to us in the question, right? So Zin will be Z0 ZL cos beta L plus J Z0 sin beta L upon Z0 cos beta L plus J ZL sin beta L. Do you have any confusion in the formula? If you have,
Clear, ma'am.
okay, clear. So yeah, so now you know Z0, you know ZL, right? Z0 is given to us where, yeah, Z0 we have found out, right? 60 ohm from question 1. We found out the characteristic impedance, that is Z0 is equals to 60 ohm. So we know that. So we will put Z0 is equals to 60 ohm, ZL is equals to 150 ohm. Other things we already know, right? बाकी का तो पता ही है, बीटा पता है, बीटा हमने यहाँ से पता कर लिया था, L हमें पता है which is equals to 60 centimeters, है ना? Or is there anything else missing? No, we know all the terms, we know the formula. We will put it in the this formula, and we will get Zn, right? It is equals to this 132.8 J 43.3 ohms. Is there any issue here? Any doubt? Yes, it's there in the this thing as well. The lecture PDF, the lecture transcripts that you get from NPTEL. So these transcripts also contain these PDFs. These formulas. The sir would have taught you already, right? Yeah. So you would be knowing this formula by now, and we will use this formula for this input impedance. Okay. Now let's go to question number 4. Question number 4 is standing waves are formed on terminated transmission line when? Okay. So standing waves are formed on terminated transmission line when? Okay. So it's asking that let's say a transmission line has been terminated, right? Terminated with a load. Now there will be either standing waves or there won't be standing waves. So it's asking the conditions when standing waves will be there, right? Can someone from you tell me what can be the answer? Okay, first let me explain the options as well. So the first option here is the reflection coefficient on the load is not 0. Okay, so here it's saying that reflection coefficient 0 nahi hai, theek hai. Second option is load and characteristic. 1 second. Okay, so do you have any problem? I can see a raised hand here. No, I don't. Okay, all right, let's go. Yeah, so first is reflection coefficient on the load is not 0. Okay, theek hai. Second option is load and characteristic impedance of the transmission line are equal. Okay, saying ZL is equals to Z0, right? Are equal. Okay. The reflection coefficient on the load is 0. Okay. None of these. So now, can someone tell me what will be the answer?
Option B. Second option.
Load and characteristic.
Okay, 1 second. You have to say one by one. Okay. So go ahead.
Whenever the load impedance is equal to characteristic impedance, then there will be formation of this
Standing wave. Okay. Why do you think that is the answer?
Because the incident wave is reflected back, ma'am.
Yeah, so it's if it's reflected back, but if load and characteristic impedance will be same, then it will be observed, right? There won't be any reflections. It will be transmitted, whole wave will be transmitted, isn't it? If load and characteristic impedance are equal. Here it's asking standing waves, what will be the condition for standing waves to be formed, right?
Okay.
Okay. uh, who else? Is there anyone else wants to try? What will be the answer?
Option A, madam.
Okay, option A. Good, good. Why?
Why? Because the reflection coefficient is and the load is not zero. For we have to connect with the source with the load means we have to maintain that reflection coefficient is zero only. Maximum impedance matching it will be happen. If not zero means the input impedance is not matching with the load impedance. So first one.
Okay, yes, yes. Very good. Yeah, so there will be some kind of reflect. If there is a reflection coefficient which is not equals to 0, which means there will be reflections, right? And if there will be reflections from the transmission line, there will be standing waves as well. है ना? So here, see. So if it's 0, then there will be no reflection. But if it is something not 0, not if the value of reflection coefficient is non-zero, then there will be standing waves. These are the condition for standing wave. All right. So option A will be the correct option. Okay. Option 3 was this one correct. Okay. Is there any doubt? Should I go ahead? Okay. All right. I will go ahead then. Okay. So question number 5. Question number 5 here says that a distortionless line. Now lossless line is not asked. Here a distortionless line has been asked. So first thing is, can someone tell me what is distortionless line? Alright, okay, okay. I will tell you what distortionless line means. So distortionless line means, let's say that there is a wave, right? There is a wave. One second. It's not like a wave like this, right? So, and it passes through the transmission line. Okay, it passes through the transmission line. Then our wave will have the same structure. Our wave will have exactly same kind of curve, all the same values, all the everything will be same. Only it will have some kind of phase difference, right? But it will be distortionless, right? The whole waveform will be distortionless. It will contain its structure. It will have the same structure as in the starting. During input, it has the same whatever the waveform was, it will contain its structure, so it won't be distorted. So this is what transmission line means. Distortionless transmission line means. Okay. So a distortionless line has characteristic impedance 50 ohm. Okay, we know the Z naught, and attenuation of 20 millinepers per meter. Okay, so we know alpha as well. Okay, we know Z naught. Okay, the phase velocity, that is mu p, is equals to 0.6, where C is the speed of light in a vacuum. Okay, 0.6 C, where C is the speed of light in vacuum. The line parameters R and L respectively are. Okay, one second. So can someone tell me how to solve this question? How to go about this question?
ma'am.
Hmm.
R is equal to alpha into Z, ma'am. First to find
What? Can you repeat yourself?
R is equal to alpha into Z.
Okay.
Attenuation constant into impedance. First you find
So
R.
can you tell me what kind of impedance? What impedance? Load impedance?
Characteristic impedance.
Yes,
Characteristic.
yes. Good, good. Yeah.
Then
Alpha
L
into
is
Z.
equal to Z divided by U, ma'am.
Ha. Yes, yes. Yes. So alpha into Z naught. We know R will be for distortionless transmission line. We have a condition. Okay, let's go and try to solve. For distortionless line, we know that RC is equals to GL, right? So if RC is equals to GL, we will shift this and we got to know that G is equals to RC by L, right? Now, we also know that Z naught is equals to under root L by C. This is for distortionless line, right? We should know the condition. For distortionless line, we know that Z naught is equals to root L by C. And alpha is equals to under root R by G. That is, from here, from this equation, we can put G, instead of G, we can put RC by L, and which it will become R under root C by L. That means R upon Z naught. So R becomes, may I know your name? Who told me the answer?
Gokul, ma'am.
Gokul. Acha. Sorry, Gokul. Yeah, so good, Gokul. Very good. So you directly told us the formula for this distortion line, which is equals to R is equals to alpha Z naught. So we will we know all the values. We know alpha, we know Z naught. We will put it and we will get R. Okay. Now we know velocity. Velocity will be equals to omega upon beta. Beta is phase constant, which is equals to, this also is given to us, right? For distortionless line, the velocity is equals to 1 upon root LC. So if we know this, we will put Z naught here, right? We can switch to this, which is L is equals to Z naught by mu, right? We know the value of mu, we know the value of Z naught, we will put it and we got the value. L is equals to 277.8 nanohenry per meter, right? 2778 and 10. This option D, right? So is there any doubt here? Or should I go ahead? Okay. If no doubt, then I will go ahead. Okay. So question number 6. Now I want, since it's a easy question, I want everyone to interact with me. Okay. Uh, I want others as well to interact with me. If even if you don't know the answer, if you know, if you have anything else, like if you have not the solution but some other kind of information you have, you tell me that. Okay, no need to worry that you are wrong or something like that. You just have to answer. You just have to say something. I just want my session to be interactive. Okay. So question number 6. Which one is not correct regarding lumped circuit regime, right? It's a lumped circuit regime. Okay. Which one is not correct regarding lumped circuit regime? First is physical dimension is far less than wavelength of the signal. Okay, here it's saying that the our physical dimension of the elements used in the circuit will have far less size compared to the wavelength of the signal. Okay. Second option is saying that Maxwell's equations can be simplified. One thing is to notice is it's asking which one is not correct. Okay. So you have to see which one is not correct. Okay. Maxwell equation can be simplified. All right. The RLC parameters are individually concentrated at discrete points in the circuit. Okay. Right. So, and option D, none of these. So tell me which one is not correct from these three statements. Take a guess. Take a guess. No problem. Yeah. So just guess what can be the solution, right? You don't have to worry. It's okay. You can be wrong as well. It's a lump circuit design. In our 11th and 12th as well, we all the circuits that we study are lumped circuit, right? It's not distributed circuit. Okay, I will first tell you what lump circuit means. Okay, someone has messaged me something. What is lumped circuit? Okay, so can you see my hands? Yeah, I think my hands are visible. Yeah, okay. So see, there are two kinds of circuit. One is lumped circuit, another is distributed circuit. Okay, so when we feed this kind of circuit with a electromagnetic wave, okay, so either this wave feels like this circuit is lumped or distributed. So what lumped and distributed means? Now lumped means that the wave has a wavelength, okay, which is too big for the circuit element. Okay, so if that happens, right, if okay, let me give you a example that would be better. Let me think about it. Okay, uh let's say a human being, right, a human being has to travel, huh? So one human being has to travel let's say 10 meters, okay, and there are lots of uh, objects placed in between this path, okay. So a human being which is, let's say, around 6 feet tall, okay, and they have to travel at 10 meters distance, okay, and different objects are placed. One thing is that, say, this human has to travel 1 kilometer, okay, and again lots of objects are placed, okay. So for this human, if, let's say, these objects, okay, in a 10-meter thing, so what do you think, for this human being, if he travels a 1 kilometer and if it travels a 10 meters, will there be a difference? First tell me that. Will there be a difference in the uh, how this human receives this path? Let's say these objects are obstacles, okay, obstacles are kept, huh? So if these obstacles are kept in a 10-meter distance, so every object for that man, or a human being, so every object in this kind of road, 10-meter path is there, so every object for that human being, every object will be uh, will have some changes in the human being, right? मैं हिंदी में समझाती हूँ. I hope everyone knows Hindi. It's going quite uh, right. What I'm trying to tell you is, see, I leave the example. I think I have went into too much complicated thing. So if there is a wave, right? You can see the wave, right? Wait, I I can try to write here. That would be better, है ना? Let's say this wave is there, है ना, and it has to travel a very long transmission line. Okay, it has to travel a very long transmission line. This, right? So
wavelength is
and
wavelength
other,
is small means it will having more losses in long distances. Long means
yeah, no,
that's
that's
the
not
things only
what
you are
I,
telling now.
yeah, no, that's not what I want to tell you. I want to tell you, yeah. So
Madam,
see this,
from first lambda which is equal to c by f is there, no speed lambda which is equal to c by f. Lambda wavelength antenna sizes increases means frequency is decreases. I think first option is correct. From that formula, I am telling first option.
yeah, but wait. It's, you are saying that first option is not correct. Is that what you are saying?
Correct, madam.
Yeah, no,
First option is correct.
but the question here is which one is not correct. Okay.
Ma'am, second option is not correct.
Why? Why do you think like that?
Because Maxwell equation is
Mm-hmm.
Maxwell, Maxwell equation is same for both lambda as well as for distributed elements.
Yeah, but here it's saying that Maxwell equation can be simplified. So simplified Maxwell
How can it
equation
be?
means KCL and KVL. Right? KCL and KVL. Simplified Maxwell means KCL and KVL. And you in your class 11th and 12th, you all the circuits that were given to you were lumped circuit. Mostly it was lumped circuit because RLC were used to be given, and you didn't used to go for distributed, right? डिस्ट्रीब्यूटेड सर्किट पे नहीं जाते थे ना, तो केसीएल और केवीएल लगा लेते थे. तो मैक्सवेल इक्वेशन सिंप्लीफाइड आर केसीएल एंड केवीएल ओनली. So here lumped circuit में KCL and KVL can also be used, right? So this is correct. The physical dimension is less than wavelength of signal. Yes, it's also correct. This is we went far into the example, so let's drop that. It's correct because what it means is that the wave, whatever wave we send through these kind of circuit, it does not transform it, it does not distort it, or it is not lost, right? So let's say you have read in your class KCL and KVL, you would have read, right? If we feed it with a far too large wavelength of the signal, okay, so the potential here and here will be same, right? It's a short circuit, so potential here and here will be same. This you would have read in your 11th and 12th. It's a short circuit, right? But if the wavelength of the wave is, let's say, about equal to the transmission line, then here, right, then the voltage, then the characteristics of this line will also come into picture, and the voltage here cannot be taken equal to the voltage here. There will be some distance, there will be some resistance, inductance and capacitance in this transmission line, and it will come there. All right, it won't be same here, even though it's a perfectly it's even though it's a if it's a copper, even then there will be some kind of characteristic of the transmission line which will affect the wave. So for a lumped circuit, to assume a circuit to be lumped, we have to the wavelength of the signal has to be far greater than compared to the dimension of the transmission line. Okay, let's go to the third option. The third option also says that the RLC parameters are in. Someone is saying something. Okay, let's ignore that noise. The RLC parameters are individually concentrated at discrete points in the circuit. I have told you this already, right? कि RLC जो भी parameters हैं वो एक discrete point पे होते हैं circuit के rather than distributed. It is, देखो यहाँ पे क्या है कि अगर ये ट्रांसमिशन लाइन है तो यहाँ पॉइंट और यहाँ पॉइंट, हर पॉइंट पे RLC बदलता जाएगा बिकॉज इसमें ट्रांसमिशन लाइन का भी कैरेक्टरिस्टिक आएगा, तो वो RLC हर पॉइंट पे बदलता जाएगा. बट अगर हम लम्प सर्किट लेते हैं तो लम्प सर्किट में क्या होता है कि RLC अगर लगा रखा है सर्किट में तो इट विल बी कंसंट्रेटेड एट डिस्क्रीट पॉइंट, इट वोंट बी डिस्ट्रीब्यूटेड थ्रू आउट द सर्किट. ओके, understood? So this is also correct that the RLC parameters are individually concentrated at discrete points in the circuit. So which one is not correct regarding lump circuit design is none of these. So correct option is none of these. All the others are correct.
Then ma'am, my question is, then how in transmission line we are measuring resistance, inductance and capacitance? But in transmission line at high frequency, we are considering resistance per unit length,
Yes.
capacitance per unit length.
Yes.
Then how we are measuring that resistance, capacitance and inductance?
So yeah, so it's distributed. So we take it as a delta L. So we integrate it. First we differentiate it and then integrate it. So we don't see it's distributed. So at every point it is changing. So we take it like that. I will show you. Have you done lecture number 59?
Yes, ma'am.
Yeah. So in lecture number 59, it's given. Transmission line steady state sinusoidal response. So our V0 will be changing with time, and it's it's complicated equations. So if you have read this, you would be knowing. If you have done the lecture number 59, you will be knowing that. Let's see. One second. Let's go to lecture number 58 as well. All right. That way. Yeah. So here, what happens is first transmission line is like this, right? And there is a substrate in between these two transmission lines. Okay, so for the transmission line, it will be conduct. It won't be perfect insulator, right? There will be some kind of conduction current as well as displacement current. So if there is conduction current and displacement current, then we can write it as some elements are there, right?
Okay, ma'am, I got it. That in transmission line in series path we have resistance and inductance, and in parallel path we have conductance and capacitance.
Yes.
My question is, but in just like in lump circuit at low frequency, we are using potentiometer for measuring resistance, or ohm meter for measuring resistance, or for capacitance and inductance we are using for some bridges. But in case of at high frequency, like in transmission line, how can we measure resistance, inductance and capacitance? Is there any instrument or?
I am not aware of what instrument is used. So it's see, and we have like different using these kind of models. Then there are applications, antennas are there, then other things are there. So but how to measure different potential, because it will be changing at every point. So
Potential.
Okay. You are talking about RL and C, right?
RL and C. Okay.
Yeah. So for RL and C, I don't have answer for this question right now. So I will try to search it and then try to tell you what will be the answer for this, because
Okay, ma'am.
it's
Thank you.
changing. Yeah. So I don't know. I have to check. Okay, let's go.
Okay, ma'am.
Okay, question number 7. Is there any other doubt you have? Anyone else? Or should I go ahead? Yeah. Anyone has any doubt? No. Alright, let's go ahead then. Okay, question number 7. For high frequency transmission line, okay, omega L is far greater than R, omega C is far less than G, okay, omega L is far less than R, omega C is far less than G, omega L far greater than R, omega C far greater than G, omega L far less than R, omega C far greater than G. Okay.
So option C, ma'am. Omega L is far greater than R and omega C is far greater than G.
Yes. Yes. For high frequency transmission line. Why are you telling what is the logic behind this?
Because omega equal to 2 pi f, na?
Yes.
So if the frequency is very high, then obviously the reactance will be high.
Yes, good, good. And same for this, right?
If the option is given like 1 by omega c, then it will be very less. Since the option is given omega c,
Yes.
that's why it is much greater than G.
Yes, yes, good. Yeah. Now let's go to question number 8. Is there any doubt? Anyone else? No? Okay, let's go ahead. Question number 8. If the characteristic impedance is same as load impedance of a transmission line, the line is called, okay. If the characteristic impedance is same as load impedance of the transmission line, the line is, so here Z0 and ZL are equal, right?
Equal. Okay.
Yeah. So what the line will be called?
Matched.
Matched. Okay, very good. Why matched?
Because the characteristic impedance and the load impedance are equal. That's why maximum power transfer will be taking place.
Yes.
That's why this is matched circuit.
Yes, matched circuit, and there won't be any standing
reflection.
Yeah,
Standing wave.
Yes, yes. No reflection as well as no standing wave. Good, good. Let's go to question number 9 then. The primary parameter which is associated with electric charges. Okay, so this question is not for a bachelor student. It can be answered by a 11th 12th student as well, right? Those who know capacitance and inductance and everything. So those students as well can tell what will be the correct option, right? Here it's asking the primary parameter which is associated with electrical charges. So first option is given to us resistance, second is capacitance, third is shunt conductance, fourth is all of these. Someone may. Okay. Which will be the correct option? Electrical charges, right? Have you ever heard about two parallel plates having charges?
Yeah, ma'am.
Right? Having opposite charges or something. Have you ever heard? Huh? I hope everyone has heard. So the primary parameter which is associated with electrical charges will be, is it resistance or capacitance or shunt conductance? What will be the answer?
Capacitance.
Yeah, capacitance. What?
Yeah.
Why are you thinking like that?
Because the capacitance, the definition is the ability of the device to hold charge.
Yes, exactly. Very good. Very good. That's why capacitance, right? Resistance and shunt conductance.
Yeah,
Basically flow.
it depends on the material property.
Yeah.
Okay.
Yes, and current flows there. So charges are flowing there, but electric charges can be stored by the capacitor. So the primary parameter associated with electric charge will be capacitance. Okay. Very good. Let's go to question number 10. Question number 10 here is a 30-meter long lossless transmission line with Z0 is equals to 50 ohm operating at 4 megahertz is terminated with load ZL is equals to 70 plus J40. Okay. 70 plus J. ZL is given to us. Standing wave ratio is asked. Okay. L is given to us, Z0 is given to us, and frequency is given to us. Can someone tell me how to find out the standing wave ratio?
So first we have to calculate the reflection coefficient, then
Right,
uh,
right. And then,
so gamma equal to ZL minus Z0 divided by ZL plus Z0.
yes, and standing wave ratio is equals to
1 plus gamma magnitude divided by 1 minus gamma magnitude.
right. Right. Now let's find out the reflection coefficient. Very good. Yeah. So first we have to find out the reflection coefficient. So reflection coefficient is equals to ZL minus Z0 upon ZL plus Z0, right? And ZL is given in the question, Z0 is given in the question. Okay, we will put it and we will get something like 0.3536. Now for standing wave ratio, we know that the formula is 1 plus magnitude of reflection coefficient upon 1 minus magnitude of reflection coefficient. We will put the values and we will get 2.094, right? Yeah. Somewhere here 2.094, option A. Okay, so we don't need to use 4 megahertz frequency. We don't need to use this. We don't need to use 30 meters long. We only needed Z0 and ZL. So sometimes these kind of information will also be given to you to confuse the students how to solve the question. Sometimes they will be giving uh, information which is not required, just so that you guys get confused and not able to solve the question. All right, so it's simple. Z0 and Z0 ZL and Z0 was given to us. By that we will find out reflection coefficient. Once we got reflection coefficient, we will put it in the standing wave ratios formula and we will get the answer. Okay, is there any problem here? All right. No. Yeah, thank you, good. Okay, so that was it for today. We have solved 10 questions today, and all the best for your week 8 assignment 8, and I hope you will be able to score as much as maximum marks there. And if you have any doubt, you can post it on my channel or post it in the uh, questions. I have already told you how to ask questions from the NPTEL team, right? Yeah, all right. So I will post this video as well on YouTube channel. You can watch it there, and if you have any doubt, you can post it in the comments. Okay, can you please repeat what you want me to repeat? Can you tell me that? How to ask doubt to NPTEL team. Okay, I can tell you that. But for others, I think you can leave the session. And all the best. Bye bye. And Kalyani, I'm going to show you how to solve the question. Okay, solve the how to ask question from NPTEL team. All right. So first you have to go to the SWAM portal. So problem solving session reminders for today. So I hope Kalyani you know how to reach here.
Yes, ma'am. Yes, I know that.
Okay. So if you know how to reach here, then here ask a question. Can you see here? Ask a question is given. Anna, go there.
Okay, okay, ma'am.
So ask the question, then you have to join this forum. Okay. See, there are students asking questions. So there would be replies as well. So okay. Here you can ask questions regarding the video as well as assignment. You cannot ask the solution directly, they won't be telling you the solutions directly, but you can ask for the concept behind the question or something like that if you have. So if you ask there, you will they will be replying you, they will be giving you answers. All right.
Okay, ma'am. Yes, ma'am. Got it. Thank you, ma'am.
Okay. Okay. Chalo.
Thank you, ma'am.
Yeah.
Thank you, ma'am.
Yes, welcome.
Thank you, ma'am.
All right, bye everyone.
Thank you, ma'am. Bye bye, ma'am.